Welcome back to the second part of this lecture. Okay, so we have already talked about the relationship between delta and step function. Now I am going to put this together. So just like I made pieces in the delta function, I can do that with any signal. So let's say I have some kind of arbitrary signal here. So what I can write that my signal is like the infinite sum from k equals to minus infinity to infinity of x of k times delta n minus k. It's like saying that every position at every value of k, I multiply the delta function by the corresponding value of x, and then I add all those guys up like this. So it's like adding all the deltas. So this is like taking a part of like the signal and breaking it into pieces. So we are going to use this kind of formalism a lot when we are going to study things like convolution. So this is one of the property, and it's related to the things which we have already studied, like decomposition of the signal with the delta functions, like we did with the unit step function. Now another property is what's called the sampling property. Now let's suppose I take another looking sum like this, which I have already showed you. First of all, think about what this means. This is like saying, okay, I have a signal. Let's think about a signal having function k like the one shown here. Now what is delta k minus n? That's like saying I have got a delta function that is shifted, that's delayed to start at n. So what do I get when I multiply the signals together and add them all up? Now so there are it's if you see here, so in this function which is delta k minus n, there are many zeros in the figure, right? So if I multiply with any of those zeros, like this is 0 here, this is 0 here, this is 0, 0 and 0 and 0. So if I multiply anything with these zeros, it's like the product would be 0. So the only time I get a non-zero answer is right at this point where the delta function is firing. So what do I get at that point? I get whatever number is that point. Like if I get if I multiply this with the delta function where it fires, so I get only this value, which is 1. Or in this case, if I multiply this point with the delta function where it is firing, I will get only 2. So what do I get at it's like I can use a delta function to kind of pick off any value from a signal that I want by multiplying it. Now which means that I would get actually the value which is at x of n. So the next thing is more kind of bookish, that's complex numbers. So we have talked about the signals and their characteristics. Now let's move to another aspect. Often we will talk about complex numbers like this, where x is the real part and y is the imaginary part, and we call this Cartesian or rectangular coordinates, and j is the square root of the -1, so something like this. So in this class I would probably be using j instead of iota. The polar version of the complex numbers is where r is like this equation, z equals to r e power j theta, where r is the magnitude and theta is the angle or phase. The key properties that define these relationships is the Euler's formula, which is defined as this: e power j to theta equals to cos theta plus j sin theta. Now here cos is the real part and sin is the imaginary part. And if I need to have explicit formulas, that's like saying, okay, if I have a point out here, I can call it x plus jy, or I can call it r to e power j theta like this. Those are equivalent ways of talking about the sample complex number z out here. and I can go back and forth between them by saying, like, if I want to go from Cartesian to polar, my r is just the hypotenuse of this triangle, and my theta is the arctangent of y over x. And going the other way around, if I know the radius and the angle I want to get, the Cartesian coordinates, then I say that x is the radius times the cosine and y is the radius times the sine. And all those stuff just falls right out of Euler's formula. We can always rederive this stuff whenever we want. Now another formula which you might remember is that if I go back to cosine theta, that's the same as this, our old buddy, which is cos theta equals to 1 upon 2 e to power j theta plus e to power minus j theta. And it's like the expansion of, if I expand this kind of stuff, then you can see that if I expand this, then e to j theta is actually cos theta plus j sine theta, and this is minus theta, so cos minus theta plus j sine minus theta. And if it's like, if you consider this, so basically we have this theta and we have this minus theta, and in this case the real parts are positive and the imaginary parts are positive and negative, which is alternative. So it becomes plus j sine theta and minus j sine theta, which can be cancelled out, and you get this 1 upon 2 times 2 cos theta, which is actually equals to cos theta. So it's kind of a proof that we can write cos theta in this form. Now it's your homework that you should prove that sine theta is equal to this based on the principles which I have already explained here. So you can just try to figure out or try to drive that how we can get the sine theta, or how we can prove that sine theta is equals to this. So these convergent formulas, you are going to need these a bunch to go back and forth from Cartesian to polar and vice versa. Now let's talk about sines and cosines. Let's talk about them for a while. So first let me talk in sinusoids. So let's talk about this in continuous time first, continuous domain. So just note what the parts of this equation are. Like this a is amplitude and omega naught is the frequency and phi is the phase. Now if I were to plot that, the signal would basically look like this. So say the phase was 0, it starts from the origin. If the phase was 0, so it should start from here, but we assume that phase is something, right? So it's like if I have phase, it means that if I add a shift, that means that the things are delayed with positive or negative amount, where the sinusoid goes back and forth between amplitude a and minus a. It's like between this a minus a, where a is the positive number always. The peak to peak period, this distance here, is 2 into pi over omega naught. And the phase shift is related to this phi. Just as a quick check, sinusoids are not shifted by phi exactly. We will talk more on this when we talk about transformations in signals. But first I do the shift in here, and then I have to scale at the end. So this is actually scaled by omega naught here. So we know from continuous time signal processing that we have the concept of low frequency to high frequency. Like if we consider this, so we have a low frequency, then we start adding frequencies and make it faster, and then we make it faster. So this the continuum from here to here becomes faster as we go down. So we go from low frequency sinusoids to high frequency sinusoids. So now we have the same idea here in signal processing, but life is little bit different and little bit easier in discrete signal processing. But I should talk about the exponentials first, as we come across them all the time. So exponentials, again sticking to the continuous time signals for a while, are basically the functions which grow or shrink in a certain way, where it's like c and a are real numbers. So if I were to write the exponential signal, let me write here. So it's like x of t equals to ce to at. So if a is positive here, and let me remind you that c is the real number here, uh, c and a are actually the real numbers here, and if a is positive, that means that the exponential is growing, and if a is negative, then it means that it is shrinking or decaying. So how do I handle this quantity where c and a are kind of complex numbers that make things like more complicated? So well, a little tricky. It's very tricky how to handle, like, let me write here. So if I have something like 2 plus 3j and e to power, okay, spare my writing for a bit because I am using mouse. I have already mentioned that. So this is minus 1 minus 2j times t, right? So this is quite complicated equation to handle, right? Does that mean something? Sure it does. And the best way to do this is to convert these numbers from Cartesian to polar coordinates. And so remember, I can always write like c is equal to the absolute value of c e to j theta, and a, I can write a as a equals to r plus j omega naught. Now how would I work this out? Then I would say that x of t is a polar version of c e to the Cartesian part of t. Like, it's like let me write it. So this one, it's like, okay, let me write here. So this x of t can be written as c e to j theta. I have already written that here. So I can write here like x of t equals to this. So this e power j theta can be written as e to power r plus j omega naught times t. So because it's c to a power t, we can just use this concept, and we can just replace the value of a with what we have here, and we can write this e to power r plus j omega naught t. And now I can say that I can separate this equation in purely real stuff and purely imaginary stuff. So purely real stuff is kind of, okay, let me just create a space. Just remove this. Okay. So the real stuff can be written as the absolute value of c e to power rt. And that's kind of saying that I have this real envelope on a sinusoid that looks like e to power j, like something like this, c e power rt. So this is a kind of an envelope. It's not drawn quite correctly, but spare my drawing. So this is a kind of a real envelope on a sinusoid that looks like e to power j omega naught t plus theta. And or a different way of saying this is that I can now write this as maybe this. e to power r. Okay. First, let me write and if I can expand it with the Euler's equation, then I can just write it here as absolute value of c e to power rt, and I can expand it as cos omega naught t plus theta plus j sine omega naught t plus theta. So what I can see here is that the real part, if I forget about j, if I just forget about this, if I forget about this term basically for a while, then what I can see here is that the real part is surely the cosine multiplied by this exponential function, and the imaginary part is similar. So what that kind of means is that if I suppose that this is the decreasing exponential, what it means is that figure like this, uh, real part of the signal is some cosine, like here is some cosine that is actually can be kind of oscillating within this envelope like this. So if r equals to 0, then I do not have any oscillation at all, just regular cosine or sine. But if r is negative or positive, then I have something here. So what it comes down to is simply c e power a to t. And this kind of complex sinusoid modulated by the last equation, but modulated by this equation here, has a kind of notion of frequency. And I cannot say that this function is periodic, but this does not strictly repeat itself. So it always changing its amplitude, but has some sense of period inside this envelope, like you will see here with the oscillating. And that's why sinusoids and exponentials are related to each other. So far we have talked about this sinusoids in terms of continuous domain, but let me explain it when it comes to the discrete domain. So life is similar in discrete time, and in a similar way we come across the signals that are kind of like this, where I have discrete time signal, that is some constant times some number to the power of n, which I think of as constant, e power beta n, where alpha is equal to e power beta. So the c term is exactly in the form of this exponential time domain signal. So I can say decompose it in some real part and some imaginary part like this. So last thing which I am going to talk about is the periodicity in discrete time signal. I talked about how in continuous time domain, how sines and cosines can keep on increasing in frequency like this. So if I look at this picture, there is nothing to prevent me from continuing to oscillate faster and faster. So I talk about cosine like 4000 hertz or 40,000 hertz. So it's like getting faster and faster, but that is not true in discrete time. Discrete time sinusoids looks different. So let's take a look at discrete time sinusoid. So discrete time sinusoid is like this. So what is e to power j omega naught? So we can write this e to power j omega naught is e to power j omega naught plus 2 pi n. So this is like I am going to take my frequency and add 2 pi to it. So in theory, the continuous time world would be a faster or higher frequency sinusoid. So I can write e to power j omega naught plus j 2 pi n. So basically this j and n is multiplied to omega naught and 2 pi. I have just expanded the bracket. And then I can just again simplify that to write j 2 pi n dot e power j omega naught n. So the ones who are not familiar with this, if the powers are in addition, I can just write it like this in multiplication form. Now in this case, now I can see that n is always an integer and we are in discrete time world now. So what that means is that, if I think about n equals to 0, like if I just draw out a circle here, this is the 4th quadrant. So if n equals to 0, e to power j is equal to 0. If e to power j 2 pi, then it's also equals to 1. You can just do it on your own. You will see that every time you change n, let it be 0, let it be j 2 pi, let it be j 4 pi, let it be j 6 pi, and let it be j 8 pi, it will always be 0. And if e power 0 is if you get e power 0, then it's equal to 1, and that means that what I get is 2 pi times any frequency. I end up getting 1. Now what I am left with is this term, e to power j omega naught n. This means that there is no kind of like infinitely high frequencies in discrete time world. We now have this idea that there is only a 2 pi wide kind of range of frequencies in discrete time, and that's good. So just in the same way, if I have omega equals to 0, that's like saying that e to power 0 n equals to 1, and so in discrete time world it's like the lowest frequency figure. This is something like this. So if I have the frequency 0, it's like always 1. So there arises the question that what is the highest frequency then? What is the highest frequency I can get? Well, the highest frequency you can get is flipping back as fast as you can go. And that's simply this signal. This is about as fast as I can make a digital sinusoid. And I can go and this is corresponding to w equals to pi. And e power, it's like e power pi n equals to 1 if n equals to even signal, and it's -1 if n equals to odd. So this is a high frequency because you are getting the alternatives, alternative frequency, like alternative ones, 1 -1 1 -1 back and forth. It's like saying that if you have this kind of quadrant, then you are, let me use another color. So it's like saying that you are hopping from here to here and here to here, and as fast as you hop, you have the higher frequency sinusoid in discrete time. So that means is that what means is that in DSP we no longer have to draw the charts of frequency that kind of arbitrarily go far on the x-axis, and we are going to draw, of course, a lot of pictures in this class, but that fundamentally look like this. So they kind of look like something like this, where I say, okay, this is high frequency for the reason we'll talk about in next couple of weeks. There is a symmetry around 0 in the frequency response. That means that I could have a filter that looks like an ideal low pass filter. And in practice, we are going to talk about how I can obtain this low pass filter with limited gain for finite impulse response filter. So in practice, the filter which we will design may look funky like this. And you may remember seeing the one like this from Signal and System. So we are going to talk about how we will design such responses. But that's the topic for another day. So basically, in summary, what we have did is we have understood the kind of introduction to signals and systems, like brief recap of that, and we have known that how the discrete time signals are different from continuous time signals, and what were the signal properties, how do we deal with periodicity, and we have studied about different signal properties like complex numbers. We have dealt with even and odd signals, and we have dealt with exponential signals. So this was a kind of a brief recap for signal and systems for what you have studied, which was in continuous time domain, and to tell you that how the life is actually easier when it comes to digital signal processing and discrete time signal processing. So from the next class onwards, we will cover some things which is purely related to discrete time signal processing, and we will just revisit the continuous time signal if we need to discuss something in context of what we have already studied and how it is different from the things which we have already covered in signal and systems. Okay. So if you have any questions, feel free to ask on Google Classroom. You can comment like here on this YouTube, and also you can ask me in our interactive session on Tuesdays. So till the next lecture, goodbye and be safe.